All right, this is the last big thing. We've covered the view frustum. We've solved it. We know how it works. There's one more thing that some of you might be thinking about. Early on at the beginning, I talked about field of view, and I didn't come back to it. So I want to come back and address that. We did cover it actually indirectly. Our equations do address the field of view, but not in the way that you might be thinking about it. So I want to cover that base. So perspective, view frustum, part 4, field of view. Okay. So let's just draw this out again. This is my field of view. And here's my, how should I draw this? Okay, first thing I'll note is that let's put my image plane in here. And I'm going to put a theta where my theta is my field of view. It's the angle. It's the angle that you can see, okay? So here's my theta. The first thing I want to highlight is, let's say I move the image plane closer or further. What happens? What happens to my field of view? So if you move the view plane further, what's going to happen, do you think? Further from or closer to the eye, it doesn't necessarily change the field of view. It doesn't change the field of view if the size changes to match. Right? So these three here, these three planes, these have the same field of view. Nothing changed. What did change? Just the distance. Sorry, resolution. So this is the same field of view, but maybe more resolution. Depends how you code it up, right? If you're in a unit space or 1 unit is 1 pixel, I move the plane forward, I get a bigger, imagine physical film, right? I have a smaller film. As I move forward, I get a bigger film so I can pack more things in. This is how cameras actually work, right? With bigger film, you get more resolution. So you set the cameras up for a full frame, you need to have a bigger plane with the same field of view, okay? So same field of view, more resolution. But if I want to actually change my field of view, then I need to change the distance to the size ratio. So the field of view changes when the distance to size ratio changes. So here, in this example up here, as I change distance, size changed with it. You get this perfect, right? Ratio match. So let me draw what that looks like. And I've actually drawn this before. I'm going to draw this field of view here. This is my image plane. And I'm going to draw this field of view here. If I have a smaller image plane at the same distance, I get a narrower field of view. So you need to play with that ratio. If I want the field of view to change with my OpenGL matrix, the near the far, it's the ratio between the width and the distance that sets up my field of view. Okay. So then how do we calculate that? So given these parameters, how do we figure out the actual field of view? How to calculate field of view, or how to go the opposite direction. Given a field of view, I want a 60-degree field of view. How do I figure out my parameters? And it comes back to geometry again. Of course it's geometry. So if theta here is my field of view, then I can make this triangle here. This is my near plane, right? This is y over 2, but this is my 0, 0. So this is my top. and this is minus y over 2. You know what, that y over 2 is confusing. I'm going to just cut that and just say top and bottom. Right? If this is the y is the height of the view plane, but negative gets confusing, I'll just call that top and bottom. Yeah, I think that's clear. Except I've screwed it up. Y over 2. All right. So then we can actually just set up, high school trigonometry. So we have this triangle. So first of all, we have the tangent of theta over 2, right? So if this is our field of view here, we want half of that, okay? So theta over 2, so the tangent of theta over 2 is opposite, which is y over 2, or top, over adjacent, which is our near clipping plane. So that's our equation right there. If I have the top measurement and I have the end measurement, I can use the inverse of tan to find out my field of view. Okay, so theta is going to be 2 times tan negative 1 of top over n. You can figure out your field of view. But often you want to go in the opposite direction too. I can just solve for top. So top is going to be n. Top is n times tan of theta over 2. I'm doing all this mentally. This wasn't prepared. I wasn't going to work through it. So let's hope there's no mistakes here. So yeah, so you can choose your field of view and get the dimensions for a given distance. Right? So if I put an angle in there, now I have top is n times some number. I choose my n, I get my top. Or I can reverse it. I choose my top, I get my n. Okay? So you can play with that. And then once I know my top, then my bottom is just my negative top. Right? So if top is that way, I'd subtract it and go the other way, and that's my bottom. Easy peasy. All right. Now this is for my y. Let's quickly talk about how it works in x. If my image plane is square, so if my image plane is square, then my left for my x is going to be the bottom in the y, and then my right is just a top. So if my top was 20 units up, it's going to be 20 units this way. Same field of view, right? So if it's symmetrical, I just take the top, use it for my, top goes to my right, bottom goes to my left. Just use the same numbers. If it's not a 1-to-1 ratio, if it's like your monitor, we have our aspect ratio that we learned about earlier in the course. So otherwise, we calculate our aspect ratio, which is our width divided by our height, and then we just use that to multiply the other results that we got. Okay, so then our right is going to be top times aspect. Once we have our right, then the left is minus right. So pretty easy calculations. You can use your tangent to go between field of view and that ratio of near plane to height. Okay, so that's it for field of view. I have a one more comment that was in my notes. So when I'm choosing my field of view, 30 degree to 60 degrees is considered natural. And that might seem random, like my spelling. But let me show you why it's not random. Just consider a person. This is you, top down, and this is your monitor, and you're sitting at your desk looking at your monitor. Your field of view here is going to be 30 to 60, depending how close you are, probably. If your game world is much wider, you can feel like you're in a fishbowl. It feels like you're looking through like a wide-eye lens. It looks kind of funny. And the same thing goes if it's much narrower, then it can be very disorienting. You feel like you can't see anything. So you want it to match roughly what you expect the person to be sitting at. And this is how we come up with our field of view for video games. I'm going to jump over to a sketch, some code, just to demonstrate some of these concepts. Where is it? Do I still have it? Aha. Eureka. Okay, so here's some code. I'm going to see if I can zoom in again, like I usually do. It's a bit small. Come on. There we go. So let's look at this code. It's just a standard processing program. I have some constants. My near plane is 1. My far plane is 1,000. So it's far away. I just draw everything. I don't care. And then that's no longer used. I hope I can delete that. Is it going to run? Yeah. Okay. So it's no longer used. So I go down here. I'm using the built-in Frustum command: left, right, bottom, top, near, and far. So I'm setting my near and far planes to 1 in 1,000. Okay. Now that sounds good. I have my near and far 1 in 1,000, and then I just move my object into the scene away from the plane so it doesn't clip, and I'll, maybe we'll see some of that. But that's just moving my object into the scene, so it's in between those near and far planes. No big deal. Now what I've done though is I can actually move that near and far, not the far, just a near plane. I can actually move the plane with plus, or this is the plus key without the shift, plus and minus. I can actually move it and make sure it stays positive. So I can actually move the plane, and you can see how this impacts my field of view. So first, just distance of 1. Just bring the sketch up. I want to bring it so you can see the window in there. So here's a picture of a cube. I can animate it. Looks okay. The near plane right now, it looks funky for a second, but it doesn't. Like when there's no depth cues, your brain can look at it backwards. So we have this plane, this rotating cube. Looks pretty good. Now what I want to do is, actually, I'm going to do something a little different. I'm going to get rid of a scale. That was meant to be commented. So I'm going to zoom in, move that near plane further and closer, and you can see what happens to my field of view. So I'm going to animate it again. So near plane gets further and further away. As the near plane gets further and further away, of course, you're with the same size window, you're zooming in, right? So your field of view is narrowing. So things appear to get bigger. How cool is that, right? And eventually, I'm zoomed in so much, I lose my perspective, and it goes toward being orthographic. Now I can go the other way. So my near plane, 6, 5, 4, 3, 2. So I'm moving the plane back towards me, back towards me, back towards me. Now as I start getting closer, and I have this super wide field of view, look, you start getting this fisheye effect. Look at that. Because I'm seeing so wide that you're getting this fisheye effect where Z's really exaggerated. Cool. Now I'm going to turn on one thing. You notice that as I zoomed in and out, it gets bigger and smaller. I didn't do the math to figure out to keep it constant, but I'm just going to put a scale in there so that it grows bigger as I zoom in and smaller as I zoom out to make it a little more easy to see. So I'm going to move my plane away, and then that's no big deal. It stays bigger longer now. But as I zoom in here, when it gets smaller so I can see it, look at that. Now you see clipping. Look at that. It hits the clipping plane. We'll talk about that in a later lecture. It hits the clipping plane, the invisible front plane, and the OpenGL decides not to draw it past that point. How cool is that? Right? Awesome. So yeah, so you get this fisheye effect as you change that aspect ratio. For the most part, you set this up and you leave it. You have a view frustum. It has the aspect ratio you want, and you never touch it again. So this code will be posted. All right, we are done with learning about the view frustum for now. Cool.